Welcome to this presentation in the series, Electronics, the Story of One Human Lifetime by David Beams and Gary James. I am David Beams, Associate Professor Emeritus of Electrical Engineering at the University of Texas at Tyler. This presentation is a continuation of our series on electrical behavior of the PN semiconductor junction. What are we going to cover here today? Well, we're going to talk about capacitive effects in the PN junction. These effects depend upon whether the junction is forward biased or reverse biased. By reverse bias, we mean that an external voltage V is applied to augment the contact potential. That is, we connect the positive terminal of the external source to the N region, the negative terminal to P. Forward bias opposes the contact potential. We produce forward bias by connecting the positive terminal to P and the negative terminal to N. Capacitive effects under forward bias are called diffusion capacitance, and capacitive effects under reverse bias are known as depletion capacitance, and today's presentation is going to concern itself with depletion capacitance. But why are we even going to do this? What's the purpose? Is it really important to a circuit designer to know the details of the inner workings of solid-state devices? Well, let me tell you a little of my own story. In the fall of 1972, I signed up for Electrical Engineering 340, which was a required course, at the University of Illinois. It was called Electronics 1, and I was expecting a circuits course that would show me how to make exotic and useful things like balanced modulators, Class C RF amplifiers, FM detectors, and so forth. I was very much into radio circuits and communication in those days. But I was wrong. Instead, I was introduced to concepts in solid-state physics with the classic text by Dr. Ben Streetman: energy bands, Fermi levels, electron and hole transport, diffusivity, mobility, minority carrier lifetime, things about which I knew nothing and about which, frankly, I didn't care to know anything. Made my head hurt. At first, I resisted the course, but I gradually warmed up to it, which was good because it was a required course. I had always seen electronic devices as sort of magic things. I knew circuit applications for diodes and transistors, but I really didn't understand what was going on inside of them. But as the course progressed, I began to understand better why these devices behaved as they did and how this was relevant to circuit designers. But not all the concepts came readily. Junction capacitance was one I never really understood until many years after my undergraduate days. So here's what I figured out and why I think it would be useful for you to know this. But before we start into that, let me ask you a question. Suppose that we have a sphere the size of the Earth, radius at the equator of 6,378 kilometers. And suppose we put 1 coulomb, that is 1 ampere second, of charge on this sphere. What would the electric potential of this sphere be? Would it be 15.9 microvolts? 1.41 kilovolts, 28.4 millivolts, or 1/4 pi megavolts? We'll answer this at the end of the presentation. Let's review the geometry of the simple PN step junction. We have a block of uniformly doped P-type material with N sub A acceptors per cubic centimeter, and it is in contact with a block of uniformly doped N-type material with N sub D donors per cubic centimeter. The junction has a cross-sectional area A, and a depletion region forms at the junction, as we've seen in a previous presentation. And the depletion region we'll assume extends from minus X sub N to 0, and on the N side, and from 0 to X sub P on the P side. And this charge separation, this charge dipole, positive charges here, negative there, produces an electric field. And the integral of electric field with distance gives rise to the contact potential, which we found in a previous presentation to be kT over Q times the natural logarithm of NAND over Ni squared, where K is Boltzmann's constant, 1.3806 times 10 to the minus 23 joules per Kelvin. T is absolute temperature in kelvins. Q is the unit electronic charge of 1.602 times 10 to the minus 19th coulombs. N sub I is the intrinsic electron-hole pair concentration of the semiconductor, measured in electron-hole pairs per cubic centimeter. And KT over Q has a value of 25.9 millivolts at 300 kelvins and is sometimes referred to as the thermal voltage. We're going to start by exploring charge storage in the junction at equilibrium. Then we'll consider how this charge storage is affected by applying a reverse bias. And we'll use charge storage versus external potential to find the junction depletion capacitance. We'll begin by finding the width of the depletion region and the electric field that's found inside the depletion region. We assume that electric displacement flux emanates from isolated charges from a positive charge toward negative charges. Lines of electric flux extend from a charge until they terminate on an equal but opposite charge. Gauss's law of electrostatics tells us that the closed surface integral of d dot ds is equal to the enclosed charge, where d is the electric displacement flux density, and it's a vector quantity, and d sub s is a vector normal to the closed surface, which has a length d sub s, or an incremental length ds, which is represents an area on the surface, an incremental area of the same ds. In this geometry, though, the electric flux extends from positive charges on the n side to negative charges on the p side. The flux is one-dimensional, x direction only, which means that since it's unidirectional, we'll treat the flux density as a scalar. It just simplifies the math. So let's start with the n region beginning at minus x sub n. There are no unpaired charges, hence the displacement flux exiting this face of the block is 0. Now let's add a slice of the depletion region with delta x. That adds uncompensated charges and gives us an electric displacement flux density of QND delta x. Now if we add another slice of the depletion region with delta x, that doubles the electric flux density because we now have twice as many charges in this volume, but the same area through which the displacement flux passes. If we continue adding slices until we reach the end of the n region, we get an electric displacement flux of QND x sub n. Now, if we add a slice of the depletion region on the p side, again of width delta x, now that contains negative charges. The negative charges in this slice cancel some of the positive charges, leading to a reduction in d. And if we continue adding slices of the depletion region on the p side until we get to x sub p, all charges are matched. The total positive charges contained in this volume equals the total negative charges in this volume, and the electric displacement flux is 0. So if we look at the displacement flux profile within the depletion region, it follows a triangular profile with its maximum value, d max, occurring at x equals 0. The metallurgical junction between the P and the N regions. But D outside of the depletion region is 0, so that allows us to have an alternate expression for D max of Q NAX sub P. And if we equate these two, then we can relate X sub N and X sub P to the doping densities. The average displacement flux through the depletion region will be half of the maximal value because of the triangular profile of D. So the average electric field in the depletion region is found by dividing the average electric displacement flux by the electrical permittivity of the semiconductor, where epsilon sub naught is the permittivity of free space, 8.854 times 10 to the minus 14th farads per centimeter, and epsilon sub r is the dielectric constant of the semiconductor material. And the average electric field multiplied by the total width of the depletion region, which is x sub n plus x sub p, gives us the contact potential. We just have to have a way to compute W, and we'll start by working on finding x sub n. Now, we can start here. The contact potential is this term represents the average electric field strength, and this is the total width of the depletion region. And here I've just made a substitution. I've replaced x sub p with an equivalent expression in x sub n. Now it's just algebra. This is a repeat of the last expression on the preceding slide. We find a value for x sub n, and now by multiplying it by a factor which is 1 plus nd over Na, essentially, we find the total width of the depletion region, and we come up with this compact expression for the width of the depletion region in terms of the contact potential and the doping densities and the electrical permittivity of the semiconductor. Well, we're engineers, we like to see numbers. So let's take a silicon junction with 10 to the 17th acceptors per cubic centimeter on the P side, 10 to the 16th donors per cubic centimeter on the N side, 300 kelvins. That gives us a contact potential of 756 millivolts. The dielectric constant of silicon is 11.7. And we get a width of the depletion region of 328 nanometers, which for reference purposes, that's about half the wavelength of red light. And if we find the average electric field within this depletion region, we get 23 kilovolts per centimeter, which is quite a hot electric field. Now, let's find the total charge Q stored on each side of the depletion region. So Q, capital Q, uppercase Q, is lowercase q, the unit electronic charge, times the area of the junction times x sub n times n sub d. And we can derive this expression for the total charge stored on one side of the junction. Of course, we could have started with uppercase or total charge. Uppercase Q is equal to the unit electronic charge times area times the penetration into the P region times n sub a, and we'd have gotten the same result. Now let's define the equilibrium depletion capacitance CJO as dq dVO, d capital Q, I should point that out. And if I carry out the differentiation, we get this expression, and we define the equilibrium depletion capacitance in this way. We're linearizing the capacitance around the point VO. So let's do some numbers. Silicon junction at 300 kelvins, 10 to the 17th acceptors per cubic centimeter, 10 to the 16th per cubic centimeter donors in the N region, dielectric constant 11.7, contact potential 756 millivolts, and we get a capacitance of 31.6 nanofarads per square centimeter. Now let's assume we have an external potential V that augments the contact potential. So we add that in the denominator for the expression of capacitance as a function of V. And by simple algebra, we can derive from that that's equal to the equilibrium junction depletion capacitance divided by 1 plus V over V naught. Let's do some numbers now. Silicon junction again, with the same doping densities, same dielectric constant, same contact potentials we had before, and we see that as a function of the reverse bias, see how the capacitance per unit area changes. It decreases as we increase the reverse bias. So we see that the junction exhibits voltage variable capacitance, which tends toward CJO multiplied by V naught over V to the half power for voltages much larger than VO. But okay, is there a practical reason now we should care about the capacitance of reverse bias junctions? Well, here's one example. Here we have a cross-section of a CMOS logic converter, which is the basic, it's the simplest logic block in today's dominant digital technology. Here's the output node, and you see we have two reverse biased PN junctions that are connected to the output of this digital logic gate. Here's one, here is the other. These capacitances limit the switching speed of this logic gate. The greater the capacitive loads, the slower our CMOS devices will switch, the slower our computers will run. We want to minimize these so-called parasitic capacitances to obtain maximal speed from our logic devices. But there are applications where instead of the capacitance being an unwanted parasitic complication, there are actually applications where we can make use of capacitance of the reverse bias PN junction. We can use the junction capacitance of what are called varactor diodes for electronic tuning of radio circuits. We can exploit the voltage variable capacitance characteristic of the junction. So this is a simulation of a resonant circuit, LRC, that involves a varactor. V2 here is the input signal source. The measured output voltage is going to be taken here at node 1. And V1 is a DC biasing source used to establish the reverse bias on the varactor diode. And these are plots of the resonance peak of this LRC circuit. The resonant peak is at 7.1 megahertz when the DC control voltage is 1 volt. But at 5 volts, it shifts to 9.5 megahertz. So we draw the following conclusions here. The capacitance of the reverse bias junction is the depletion capacitance. Varying the applied bias changes the stored charge in the depletion region, hence the name depletion capacitance. It can be a parasitic element, that is not a designed element, not a wanted element, that limits the switching speed of digital logic circuits, or can also limit the usable frequencies of amplifier circuits. But there are applications where the voltage variable depletion capacitance is exploited in circuit design with devices called varactor diodes. Varactor diodes are used for tuning of radio frequency voltage controlled oscillators or in direct generation of FM signals. Now about that potential of the Earth. If we place a charge of Q coulombs at the center of the sphere, the electric displacement flux at the surface of the sphere of radius r is d of r is q over 4 pi r squared, total charge divided by the surface area of the sphere. The electric field then, we find that by dividing q by the electrical permittivity of free space, and that is equal to minus the derivative with respect to r of the electric potential. And the electric potential b of r is this integral running from infinity up to r of minus q over 4 pi epsilon naught rho squared d rho, where rho is just a dummy variable of integration. And the electric potential at the radius of the surface of the Earth is q divided by 4 pi epsilon naught times r sub e. Let's put some numbers in the formula. 1 coulomb, 8.854 times 10 to the minus 12 farads per meter for epsilon naught. And RE is 6.378 times 10 to the 6th meters. The potential at the surface of the Earth is 1.41 times 10 to the 3rd volts, or 1.41 kilovolts, which is surprisingly large, but that's what the numbers show. So the correct answer was B. The capacitance of the Earth, charge divided by voltage, is then 710 microfarads, which is less than the capacitance of this device, which is a 750 microfarad, 500 volt rated electrolytic capacitor. It's strange, but true. And it's not the only strange but true thing that we're going to encounter in our engineering professions or in life in general. Anyway, we appreciate your attention. We hope it has been worth your investment of time and attention, and we look forward to seeing you in our next presentation.